All right, let's begin. Um, I'll get started off. All right, everyone, welcome um, to the third workshop in beginner track. Um, if you're here, glad to have you here. We're gonna today we're gonna get started with logistic regression, but before we get into it, just a quick reminder that ACM internship applications um, are live, and the link, as you can see, is on the slide right now. Um, Please, we encourage everyone to apply. It's a great opportunity to get involved with ACM, and it's a pretty good it's overall just like a really good way to get involved with ACM, understand how things work behind the scenes, and like help out all at the same time. Yeah. So yeah, just so the link again is on the slide. Go ahead and apply. It's fun. All right. Let's move on. Yeah. So today, before we begin, just gonna go ahead and start with a quick recap of linear regression, because logistic regression, which we're going to do today, is going to kind of like stem from linear regression. So yeah, just a quick recap of what we did last week. So next slide. Oh yeah, so linear regression. Our main goal with linear regression was finding a function, and more specifically a linear function, that can essentially predict an output given a set of inputs that we provide to the model. And when we dealt with linear regression, our outputs were continuous. That means they occupied like any value, any real number essentially, and that is essentially that why we call it regression. Today we're gonna take a look at logistic regression, which is technically a classification algorithm, but it is known as, it's still called logistic regression. Yes, a small caveat there, but we're going to be taking a look at classification today rather than regression. Next slide, please. Yes, if you guys remember, the hypothesis function for a linear regression is, as you can see above, it's essentially the sum of all these different products, weight into a particular input value, and a bias. So the set of all inputs, x1 through all the way through xn, are usually contained within an n-dimensional vector, where n is a number of features in the example. And if you don't remember what a feature is a property of whatever we're trying to measure. If you remember last week, we were dealing with housing prices. So features are the different aspects of houses that affect the housing price. So yeah, every single feature will have a corresponding input value, x1 to xn, and that can be essentially anything. Like, for example, how old the house is, it'll have some value. The number of rooms it has, that's going to have another value. And again, the weight is also going to be an n-dimensional vector. Each weight corresponds to a particular feature, and the weight for a particular feature tells us how important a particular feature is to the price of the house, if we're going to use last week's example. So yeah, and yeah, the last thing, the bias is just to essentially shift our output from our model so that it fits the predictions that we expected to give. So yeah, next slide, please. Yeah. So the main way we learn our weights in linear regression, and essentially any like machine learning model is using the loss function. The loss function gives us an opportunity to assign a numerical value to how bad our predictions are compared to what we expect the actual output of the model should be. So as you can see here, y hat I is the output of the model or the prediction, and for a particular set of inputs, and y sub I is the actual value we were expecting. Um, and as you can see, the subscript I is for any training sample I all the way until M, where M is the maximum number of training samples. Yeah, yeah. All right, cool. And yeah, and the way the learning happens, where the way all the magic happen is through gradient descent. And the gradient descent for the loss function are the equations you see on the screen. Um, the way you kind of derive each one is pretty simple. You just kind of have to like differentiate the loss function with respect to every single weight and the bias, and you're going to get the equation in front of you. And we can use the partial derivatives of the loss function with respect to every single weight and the bias to begin to actually apply the learning process, where as you can see on the right column, we have w sub j is equal to w sub j minus alpha into the partial derivative of the loss function with respect to wj, where alpha is the learning rate, and we use this equation. So technically, the left hand side of the equation should be w sub j new, and the right hand side should be w sub j old. So you're kind of like updating the weight using the partial derivative to get to the weight that we want to use in our model. So yeah, let's move on. Before we begin the poll, are there any questions related to linear regression? Anything about gradient descent, the loss function, anything? I'll give it a few minutes. Oh, no, not a few minutes, sorry, like a few seconds. Let's see if there are any questions. Okay, does regression always refer to continuous output? Yes, regression does always refer to continuous output. Um, as you'll see today, logistic regression also is called regression, although it is considered to be a classification algorithm. Um, it is a small caveat. I'm not too sure why. Um, this is just speculation, but it might be the fact that we still technically, like in the logistic regression process, we still get a sort of continuous output, and we kind of squeeze that output to either fall into one category or the other. In the case of binary classification, where we have like either we have a 1 or a 0. But like we'll get into that in this workshop, obviously. But yeah, if you want, go ahead and do just give it a search. Why is logistic regression called regression? I think you'll get a pretty good answer. All right, what is M? Okay, I think so. Then can you just move up to the previous slide, or whoever is like using the Where is controlling the screen?
Wait, give me a second.
Yeah, no, take
Trying to
that.
quit. It's not letting me.
Wait, you can't go up?
I'm using like escape, but it doesn't work.
Oh, snap.
Wait, do I have to finish this? That's weird.
Maybe like Alt F4, or I'm not really sure what's all going on.
Function.
Command W.
Oh, there we go.
Okay, there you
Yeah.
go.
Oh my god.
Sorry, that was a
Yeah. Very cool. Yeah, that was weird. I don't know what happened there.
Yeah.
Yeah. So the M. So M is the total number of training samples in that we're using to train our model. So you can think of like essentially a huge set of M vectors, M input vectors, and that's essentially the total number of total number of training examples that we're using to train our model. So if you look here, when we sum from I to M, we're saying is what we're saying is take every single training example, right? Get the prediction, which is y sub I hat, and y sub I, which is the label for whatever output, for whatever set of input you want. What is the true output and what is the prediction, and multiply that with the actual set of input values that we want to use. So yeah, M is just the total number of training samples. What were the differences between the two functions you showed? You may have covered it. I came a little late. Two loss functions. Okay, so we don't have two loss functions. We have a single loss function, but we have, from that loss function, we kind of get a gradient vector. And if you don't know what a gradient vector is, it's essentially just a vector containing the partial derivatives of all the you could say like independent variables in the function. So when you so we have a single loss function, right? And we find the partial derivative of that loss function with respect to every single weight plus the bias. So technically, the two equations you see on the screen right now, these are not the only two equations we use in gradient descent. When we say W sub j, we're referring to some arbitrary weight. And we might have hundreds, like 200, 300, whatever number of weights. And we need to calculate the loss function, the partial derivative of the loss function with respect to every single weight, to kind of understand what new weight do we need to get to using this partial derivative. So we don't have two loss functions. We only have one loss function, which is the function we saw on the slide above. I don't know, Jenson, can you move to the slide above? Or is that like, okay, so that's, yeah, so this is the only loss function we actually use. And from this loss function, we get a whole bunch of partial derivatives that we use to actually train our model. Okay, does the loss function really mean how we calculate MSE? Okay, so MSE is mean squared error, right? And that's just the name we assign the loss function, because there's a range of different loss functions. You're going to see a new loss function used today in logistic regression. But so MSE is just one type of a loss function, and the name kind of tells you everything. It's the mean squared error. So you square your error, which is the difference between your prediction and the true value you expect from the model. You square it, and then you take the mean, which is where you divide it by m. So yeah, we're gonna look at a new loss function today. But yeah, MSE is just one loss function we use in linear regression among many others. Yeah, does capital J stand for loss function? Yes, that is, yeah, a little bit of confusion there between this slide and the next one. But yeah, usually people, we can use L for loss, J. I've seen people use C for the loss function as well, because sometimes the loss function is referred to as the cost function. So sometimes I've seen people use C as well. So yeah. All right, if there are no more questions, we can move on, have a quick poll here. Oh, why do we multiply the difference between expected and actual target by the input value when computing the partial derivative with respect to a weight? Okay. So it seems complicated at first, but once you think about it, all we're doing here is we're calculating the partial derivative of J with respect to some weight W sub J. And if you actually take a look at the loss function and differentiate it with respect to that weight J, then you'll realize we are supposed, so if you think about it, we have our loss function is the sum from I to M of y sub I hat minus y hat squared, which is the mean squared error. And when we differentiate that, we bring the 2 to the bottom. The index changes from 2 to 1, and then you have to differentiate what's inside the brackets. And we know that y sub I is just the label, and that label is just a constant, so that goes away. And y sub I hat is essentially a function containing all the different weights plus the bias of our model. And when we differentiate that function with respect to a particular weight, like let's say W sub J, then all other terms that does not contain W sub J becomes 0, and the coefficient of W sub J, which is actually going to be X sub J, will remain, which is why you see us multiply with X sub J. We also have the I because you have to sum from, we have to sum over all the training samples. So that's why we go all the way from I to M. So yeah, hope you got that. If you're still confused, or if anyone is confused regarding that matter, stick around after the workshop, and I'll kind of pull out my iPad and kind of derive it for you and show you how that goes. So yeah. All right. Doesn't seem like we have any more questions, so let's get to the poll. Yeah. All right. Pretty unanimous answer here, and that's a good thing. everyone is right. So yeah, good stuff. If you look at the other options in the poll, determining whether an image is a dog or a cat, whether a tumor is benign or harmful, those are examples of logistic regression, i.e. classification, which we're going to learn today. And creating Siri is just like another ballpark. We're talking NLP, natural language processing, all that fun stuff. So, so yeah, good stuff. Predicting MCAT scores based on college GPA. MCAT scores is a continuous output, and hence it is linear regression. Cool, good stuff. All right, let's move on. So yeah, today, as we said, we're gonna take a look at logistic regression, and the motivation behind logistic regression is that we want to classify things. We want to put things in groups. And there's usually, we have two different types of logistic regression. We have binary and multi-class. Today's workshop, we're going to look at binary. And in the next workshop, we're going to be taking a look at multi-class logistic regression, which is going to be a little bit more math heavy. So yeah, linear regression, again, as we discussed, predicting continuous data, while logistic regression technically still produces a continuous output. It's just that we kind of use that output we get to calculate a probability of whether the input we give is supposed to be in one class or the other class, and you'll see how that works in a few slides. So yeah, moving on. Yeah, so example of classification tasks, as we saw in the poll, tumors either being benign or malignant. So we're talking about providing a model with maybe a picture of a tumor, and it kind of like figuring out whether it's benign or malignant, as well as numerical digits. And actually the numerical digits one, classifying digits into their numbers are is actually a pretty popular way of getting introduced to neural networks. And in a sense, and don't delve too deep into this, but in a sense, logistic regression is almost similar to like a one-layer neural network, which is like the most simplest of neural networks. But yeah, don't get too much into it, but there's just like a small tidbit for you to keep. Yeah, let's move on. So yeah, here's examples of input and output for binary classification. So we could, for example, if we are trying to like predict if a picture shows either a cat or a dog, for example, we might provide a picture as the input, and what's going to happen is every single pixel of the image will essentially be an input value. So that's sort of like the pixels of a particular picture, for example, could be made into a vector, an n-dimensional vector, if you have n pixels, with a particular value assigned for every single pixel. So in this area, so stemming from that, we could treat every single pixel as its own feature. And after we apply the model, we either find out if the picture shows a cat or a dog. And we're going to see how that works in a bit. Moving on. Yeah, hot dog versus not a hot dog. Okay, so here's something where a situation where we can use logistic regression. So let's say we want to predict if it's going to rain or not. Let's think of some of the features we would want to like use in that model: location, temperature, wind speed, all the stuff that you see on the screen right now. And yeah, the question goes back to, given these features, how would we determine whether it's going to rain? Because some of these like features you see are continuous, like temperature, while stuff like location and whatnot isn't. How do we figure out how do we figure out what the output of the model should be? Moving on. Yeah, we're going to use logistic regression. Let's assume we get this data. We're saying, okay, location is Los Angeles, temperature is 105 Fahrenheit, and everything else. And the question we ask in logistic regression is it likely to rain or not to rain? It very rarely does a logistic regression model say with 100% certainty, like it is going to rain or it's not going to rain. That's not how it usually works. What usually happens is the output of the model is going to be a probability. Is it likely to be in this class or in this class? Is it likely to rain or not rain? Is it more likely that the image is a cat or a dog? So yeah, we're dealing with probabilities, and we say that, like in this example, we're going to say that if the data suggests it's going to rain with a probability of more than 50%, it will rain. Or in this case, based on the data, we're going to get a probability that it's going to rain. The probability it's going to rain is going to be less than 50%. So we're going to kind of classify this set of data as a not rain example. A question. If the output is a percent, doesn't that make the output continuous, not binary? Yeah, okay. So that's kind of where I was coming from when I talked about the whole like sort of caveat where logistic regression is called regression, but it's technically classifying stuff. Think of it like this, and you'll see this as we go on through this workshop. I just kind of mentioned it earlier to like throw it out there so people get like ready for it. One of the intermediate steps in the entire model is it is a continuous output. But at the end of everything, the output we get from the model is either going to be 1 or 0. Like either of two options is going to be the actual output of the model. So yes, you're right in the sense that one of the intermediary outputs are continuous, but the final output is not continuous.
Sorry.
So yeah. No, don't worry, you're good.
Do you still want to like keep talking or?
Yeah. So I mean, yeah, that's pretty much it. Are there any other questions before we move on? All right, so another one. So the final output is categorical, but based on a probability, precisely. That is exactly right. Yeah, so Sudhanshu said it pretty well. If the probability you get says that, hey, the probability is 90%, then we're gonna say like, okay, if the probability is 90%, essentially greater than 50%, we're gonna say that, hey, it is gonna be in this particular category, in this class, usually a 1, and if the probability we get is gonna be less than 50%, it's gonna be assigned to be in class 0, whatever class 0 ends up being. Even on the slide you see right now, based on the data we see, we're more likely to predict that it's not going to rain. Maybe we're going to say like based on the data we get, it's going to maybe rain. It has a 30% chance of raining, for example. And since that 30% is less than 0.5 or 50%, we're gonna categorize this data to give us an output that predicts that it's not going to rain. So yeah, I'll hold on a bit more for any other questions that come by. Okay, if the model has a probability 0.5, what would the output be? So 0.5 is on the edge, so it could go either way. I believe it's based on how you kind of design the model to be. So if you want to say that, hey, the model, if the model has a probability of 0.5 or 50%, either take on class 1 or class 0. I believe that's something that's left up to whoever is designing the model. So yeah. All right. Good stuff. Yeah, if you have any more questions, feel free to stick around after the workshop is over, and we'll all go through all the problems together. So yeah, cool. I'll hand it off to whoever is taking on next.
All right, so those are some really good questions. So, like, I guess what I want to say is like, you guys can feel free to unmute yourself to ask your questions. I think that'll make it like more interactive. All right, so for logistic regression, so what we essentially want is our hypothesis to be a function that learns between a boundary between the two classes. So if this green line here represents the probability function, like, well, besides the fact that it goes like outside of like 0 and 1, like the x-axis is like the outputs that we want to classify our probability function into. But as you can see, like a linear model is not really suitable for this job because, like, first of all, like the ranges of this linear function is like -infinity to infinity. So that's a problem because our output is binary. And second of all, like, I think when the probability is about like 0.5, as someone mentioned earlier, like the output is kind of ambiguous and like the error here is pretty big. So the solution to this is to activate the output of our previous linear function using a non-linear function. So what this basically means is we want to pass the output of our linear model from a linear regression into a special non-linear function called the activation function to make our, I guess, model look more like this, which, you know, like minimizes the error to our supposed output, I guess. All right, so there are actually like a number of different kinds of activations functions available. For our workshop, we're going to be using the sigmoid function because its range is between 0 and 1. So that is really convenient because we're doing binary classification. So we're classifying between two classes. So the output of this is ideal. For those of you who are not familiar, the sigmoid function is basically just 1 over 1 plus e to the negative x. If you can't remember this, like, it's not a big deal. I think I sometimes like look up the formula because I don't remember, but like it's not a big deal. So I guess what you want to take away from this is if x is negative, then sigma is less than 0.5. And if x is positive, then sigma is greater than 0.5. So if we go back to the weather example, like if I guess our input is less than 0.5, so I guess if our feature is less than 0, like I think we're talking about like cloud cover. If there's like not a lot of cloud cover, like the probability of this is gonna be less than 0.5, right? So I guess sigma kind of represents the probability. So if it's less than 0.5, we're gonna classify as not gonna rain, and and vice versa. If this function is positive, then we're gonna classify it as is going to rain because it's more likely to rain than not gonna rain. All right, is there a question here? Okay, I don't think that's a very important question.
I was just wondering so would you redefine all your variables so that the extremes are on the negative and positive ends? Like you'd have 0 be medium cloud cover, and then -6 is no cloud cover, and 6 is a lot, or something
Yes,
like that?
that's one way of doing it. Or you can just like, like shift the sigmoid function to the right if you don't want to redefine it. So like if you can like add a bias to this sigmoid like 10. So like this whole function just like shifts to right by 10. So I guess like it really depends how the variable is defined. Like cloud coverage is, if it's 10 is a lot of cloud coverage, then maybe like you want to classify that as like it will rain. But if like it's not a lot, then you could classify it as not gonna rain. So I guess like adding a bias to the sigmoid function would be one way of doing it. Or you can like shift your data, but that's usually not the ideal solution.
That makes sense. Thanks.
No problem. Okay, any more questions before we cover other activation functions? All right, so hyperbolic tangent is kind of similar to the sigmoid function, and I forgot to mention, but like sigmoid is ideal for classification, and so is hyperbolic tangent, because like the range of hyperbolic tangent is from -1 to 1 as well. So this is also ideal for binary classification because you can just define -1 to be one of the classes and 1 to be the other class, if that makes sense. Like you don't always have to like classify like 0 as one class and 1 as the other class. You can like define an arbitrary value, I guess. That's also the case when you're doing like multi-class classification, by the way, where you have like different like numbers representing like multiple different classes. So just as a refresher, the formula for hyperbolic tangent is e to x minus e to -x over e to x plus e to -x. So I guess the most important takeaway is if x is negative, then hyperbolic tangent is also negative. And if x is positive, then hyperbolic tangent is positive. So like the sigmoid function, like I think this activation function is ideal compared to something like a step function. So like just a function of a step at some point is because activation function like hyperbolic tangent is like pretty smooth. Like the shape of this function is smooth, so it's ideal for gradient descents because it's continuous and differentiable like everywhere, compared to like a step function where you have like a sudden increase at some point. So that makes like gradient descent like really difficult. So the last activation function that we're going to cover is rectified linear unit, or ReLU. So this is pretty commonly used for neural networks as opposed to like logistic regression or classification. And ReLU is basically just like defined as the maximum between 0 and x. So if x is negative, then ReLU of x is 0. And if x is positive, then ReLU of x is just x. So I guess like the reason why this activation function is used so commonly in neural networks is because like biologically speaking, this kind of represents like how a neuron actually works. So like if the activation of a neuron is like low or negative, then it's not gonna fire at all. So it's represented by a 0 section. And if the activation of a neuron is above a certain threshold, then it's gonna fire, but then like the strength of a signal is also like dependent on like how strong the input is, if that makes any sense. All right, so I know I covered like a lot of stuff just now. So if you guys have any questions, like feel free to ask about like activation functions, then now would be the time to ask.
I have a question. So is there like specific situation where we want to use sigmoid function instead of like hyperbolic tangent, or like, or the other way around? Like, because I saw like, I think they're like really similar, except like one is like 0.5 and one is 0.
All right, that's a good question. So the general shape of the two functions is kind of similar, but I guess one advantage for a sigmoid is like it's computationally cheaper. So there's only like one exponential compared to like 4 exponential, but like the shape of these two functions is similar. So I guess how you would determine which one to use is probably through like experimentally speaking. Like you can try out each activation function and see which one performs better. But yeah, in most cases for classification, like these two functions like work pretty similarly. If that answers your question.
Yes, thank you.
Yep. Okay, I see some activity in the chat. Oh yes, Sudhanshu, if you want to like clarify.
Yeah, I
something,
wanted to
then
quickly
go ahead.
mention, the reason we often use tanh instead of sigmoid, right, is like you mentioned, the midpoint is at 0. So if we have data that's normalized, that's has its mean at 0, tanh kind of lends itself really nicely to that problem because everything ends up being centered over 0. So that's why tanh is actually really commonly used in industry. And sigmoid, the main advantage is, like Jenson mentioned, is between 0 and 1. So it naturally means something that looks like probability. So I just wanted to quickly interject with that. Thanks.
Yeah, thank you, Sudhanshu. All right. I guess if we're all set, then let's do a quick poll about the sigmoid. Give me a minute or a second. All right, I know I said like the formula is not very important, but like I guess it's important to get like a intuitive understanding of sigmoid, and like I guess it's good to like, I don't know, being able to identify like what the general like format of the equation. All right, let's wait for 10 more seconds. All right, most of you guys picked B, which is the correct answer. I guess for those of you that pick like C, it's not that big of a deal. You can always just like look it up. But I guess like one way to tell is like the exponential is always gonna be negative. So it's always e to the negative x, because if it's e to the x, then like this function like decrease like really quickly to 0 because the denominator is gonna be like really big. So that's one way to remember it. All right, we actually have a second poll about the ReLU. All right, You guys should be able to see the poll. If you guys have any more like questions about activation functions, then feel free to ask. We're gonna wait for 10 more seconds. All right. So most of you guys picked A, which is correct. It's ReLU is defined as the maximum between 0 and x. So if x is negative infinity, then ReLU would output 0. And if x is infinity, ReLU would output infinity. So some of you guys picked C. That's actually correct. The correct range for sigmoid, which is the activation function that we'll be using mainly in this workshop, but just keep that in mind. I guess it's not too big of a deal, but it's like good to have a understanding of like being able to tell like these activation functions apart, because like, you know, like ReLU is better for like neural networks, while sigmoid and hyperbolic tangent is better for classification. All right, Sudhanshu, you want to share screen?
Yep, let me do that. All right, you guys see my screen?
Yes.
Okay, fantastic. So now we're going to basically be talking about how we can take all these parts that we just learned about and put them together to get our final model. So if you recall in linear regression, what we did is we had our x, we put that into a linear function, and that was it. That was our entire model for linear regression. Over here, we're taking it a step further. After we get our x, we still take it through our linear function, wx plus b. And after that, we activate it using one of the functions Jenson just now talked about. And the function we've chosen for this workshop, and a function that's commonly used for classification, is in fact sigmoid, the sigmoid function. So what we're going to do is we're going to take this h of x and just stick it into the sigmoid function, like this. So basically just replace x with h of x. And what that does is gives us this total formula over here, if you want to write explicitly, where again, you just replace the x term with wx plus b. And the reason we do this, and we don't have just x, is to give us this kind of flexibility. So this bias term, like Jenson mentioned, helps us shift either the left or the right. W helps us determine how curvy this curve ends up being. Now, let's recall again what we want to do here. We're saying that given an x, we want to transform it using this function and get a value that either classifies as 1 or as 0. Or a little more broadly speaking, we want to classify it as greater than 0.5 or lesser than 0.5. So that's something to keep in mind. Now, let's again look at this function over here. This function is completely determined by what w is and what b is, right? Because everything else is just a constant. E1, obviously constants, and x is the input. So what makes this function, what the function is determined by, is this w and this b. So the way we can state formally what we're doing here is the following. Depending on what w and b are, we get a different function. So x, when passed through this function, predicts a value that's either greater than 0.5 or lesser than 0.5. I know we keep reiterating this, but this is the kind of the crux of logistic regression. If it's greater than 0.5, we classify it as 1. If it's lesser than 0.5, we classify it as 0. So I'm going to pause here really quick. Is everyone good with this? Okay. So yeah, feel free to keep asking questions in the chat though. Like we were talking, another way we can look at what our model is predicting is a probability. It tells us how sure are we, how likely is it that this x should be classified as a 1 or as a 0. It's giving us a probability. And the sigmoid function, since it outputs between 0 and 1, very naturally gives us something that looks like probability, because probability is always between 0 and 1. So we can instead state our prediction as the probability of the input being a particular class. We write it formally like this: y hat x is equal to the probability that y is equal to 1 given x. Or another way to look at it is, given x, how sure am I that y is equal to 1? Okay, so I see a question. How would gradient descent work for negative hypothesis values when using ReLU? Would you just adjust the weights or bias if the hypothesis is negative? Okay. I think I see what you mean. So let me try and go back a couple of slides. Okay, great. So in ReLU, what basically happens is the derivative at this point is always 1. And the reason that helps us is it helps us converge to this point really quickly. So you remember in gradient descent, how quickly we move depends on how large the gradient is. So it really helps us rocket down to this minimum point over here. And if we're already in this negative part, like you're asking about, then, well, we're done, right? That's exactly where we want to be in life. So we go here and we just stay here. We just don't move and we're good. So I hope that answers your question. So yeah, so just to reiterate what I was talking about on this slide, what our output is the probability that y is equal to 1 given x, or given x, how likely is it that y is equal to 1? So what do we need to find? Well, like I mentioned, this function is completely determined by what w is and what b is. So w and b become the parameters of our model. And they are what we need to end up learning during this machine learning process. And once we get w and b, we get what we call a decision boundary. Now over here, the decision boundary is simply 0. Well, if x is greater than 0, we end up in class 1. If x is less than 0, we end up in class 0. So formally, we need to learn a w and b such that when we input x into this function, we correctly classify it as 0 or 1. And how do we do this? Well, like we mentioned, we need to learn w and b. So how do we learn anything in machine learning? Well, we do gradient descent. So we're going to define a cost function and perform gradient descent on that cost function. So the cost function we use for logistic regression, like Adithya mentioned, is a little different from linear regression. It's what we call binary cross-entropy, which is a cool name, by the way. And the question naturally arises, well, why not just use linear regression? Why not just use MSE? And the answer to that question is we could, but it's not going to be very good. So back in linear regression, when you were trying to predict the price of a house, the label could be anywhere between $10 and $10 million, right? And we needed a loss function that could deal with all of this, which could deal with all of this range of values. But over here, we just have two labels. We just have 0 and 1. So why not create a special cost function that is specially designed to deal with this kind of a problem? And that's what binary cross-entropy is. So this is the formula for it, and it's often called log loss because of all these logarithms you see here. So we're going to talk about this on the next slide. So just to review notation, y hat is our prediction. That means it's a value between 0 and 1. Could be 0.1, 0.5, 0.7, whatever. And y is the true label. So it's either 0 or 1. It can be nothing in between. So now let's think, what happens to this formula if y was 1? So you see this term over here, you get a 1 minus y. 1 minus 1 is just 0. So this term ends up disappearing. Over here, we just say minus 1 times log of y hat. So all in all, this really scary looking formula reduces down to this one single term if y is equal to y is equal to 1. So now let's think about what we're trying to do here. We want y hat to be as close to y as is possible. That means we want it to be as close to 1 as is possible. That means we want to increase y hat. When we increase y hat in this term, log of y hat ends up increasing. But remember, we want to decrease loss. So what we do, we just stick a negative sign there. And overall, this term ends up decreasing. So let me repeat that. By increasing y hat, by bringing it closer and closer to our true value of 1, this entire term ends up decreasing. So our loss or our error ends up decreasing. Similarly, if y is equal to 0, this term disappears because we get a 0 times log of y hat, which just goes away. Over here, we get 1 minus 0, which is just 1. And all in all, we get just this one single expression. So similarly, let's try and analyze what happens here. We want y hat to be as close to 0 as is possible. That means we want to minimize y hat. Note the difference. Last time we wanted to maximize y hat. Now we want to minimize y hat. So how do we do that? Well, we're going to change this function a little bit. By decreasing y hat, 1 minus y hat ends up increasing because of this negative sign over here. If 1 minus y hat increases, log of that term increases. And like before, we put a negative sign in front, which ends up decreasing the overall loss. Okay, so I'm going to pause here because I know that this is a complicated looking function and it definitely takes a couple of looks to get it right. So does anyone have any questions?
Yeah, I have a question.
Yeah, go for it.
So why do we use log over any other function that would preserve that relationship between y and L?
Okay, that's a good question for sure. So I think the reason is it's a little more involved, and basically means that when you formulate your problem like this, when you say that this is going to be my loss function, it helps produce a nice, smoother minimum and helps us learn it a lot faster. So the choice of log could have been replaced by something else, like you don't even have to have the log for all intents and purposes. But the two things that it helps with is it introduces some kind of non-linearity because the log is a non-linear function. And secondly, it helps formulate the problem a little more nicely. So if you take optimization, right, it produces a nicer optimization problem.
Okay.
So I hope that answers your question. Cool. Any other questions? Okay, so let's move on then. So now what we did on this slide was we essentially calculated the loss for one of our training samples, just one of them. So we had one y hat, and one x. And it's telling me what is the error for this particular sample. We want to generalize this and take all our samples. So the total cost is, well, surprise, surprise, just summing up all the individual costs. So we just take one sample, calculate the loss for it, and add it to our total cost. And for good measure, we add a 1 over m just to calculate the average. So if you want a nice, complete looking formula, this is what it is. It's a little scary looking, but it's just calculate the loss for one sample and sum it all up. So let's do a poll here. Just tell us which is the correct formula for the loss function. Okay, I see a question here. How do we know the loss function can't be negative? Okay, that's a good question. So let me go back and go over here. Okay, so let's look at this. Let's look at just one of these pieces. The other piece will be equivalent. So y hat is a value between 0 and 1. That means that log of y hat is a value between negative infinity and 1. Negative infinity and 0, because log of 0 is negative infinity and log of 1 is 0. So we have a range negative infinity to 0. And putting this negative sign in front, the range ends up being 0 to positive infinity. So I hope that answers your question, because the way we formulate this loss function, it can never be negative. Okay. So yeah, let me run this poll real quick. We're just asking you what the correct formula for this log loss function is. And the objective isn't to kind of get you to memorize the formula, but just kind of think about it more intuitively. Because as we mentioned, one of these terms is going to end up disappearing. So we need to be, so you can usually reason through it and think about what the function should be. Okay, just going to give it 10 more seconds. Okay, let me stop here. So that's awesome. A lot of you got the correct answer, which is in fact B. I see a few of you mentioned C, and the trick here is that you're missing the negative sign. So the negative sign is what helps us create this nice decreasing loss function. And okay, I see a question in the chat. Oops, sorry, I forgot to share the results. But yeah, like I mentioned, a lot of you got the correct answer. So that's great. Sorry, can you repeat the answer to the last question? Okay, so yes, let me do that really quick. So what I said was that this function, the way we formulate it, it can never be negative, because y hat is between 0 and 1. That means log of y hat is between minus infinity and 0. And if we put a negative sign, the interval gets flipped. So we end up getting 0 to infinity. Okay, I hope that answers your question. So now let's talk about how we do gradient descent. So to recap, we have W and B, which are our parameters. And the way we want to update them is using this loss function that we just came up with. And the way we do that is through gradient descent. So we're going to take the partial derivatives of our loss with respect to W and with respect to B. And we get two different gradients. So this is the gradient with respect to W. Again, scary looking formula, don't worry about it, you can always look it up. But the point is we get our partial derivative. And using the partial derivative, we update the value of W. So we say W new is equal to W old minus the gradient. Similarly for B, we get a scary looking formula, but the point is we use this gradient to update the value of B. So our new B is our old B minus the gradient. And we keep doing this. We keep doing this over iterations. And we get closer and closer and closer to that minimum. So that's the way you get the best possible W and best possible B. So a quick note here, we've written everything in matrix notation. If you remember back in linear regression in the last workshop, we had all these ugly sigmas going around, xi, xj, xij, wij, all that stuff. So matrix notation just makes it a lot cleaner. Question, why do you subtract the partial derivatives? Okay, so the reason we do that is this algorithm that we talked about last time called gradient descent. And what that basically tells us is if you want to find the optimal solution, we need to go in the direction of the negative gradient. So we go in the opposite direction as the gradient, and we put this negative sign to do that. So I definitely suggest looking over our last workshop slides as well, but that's the basic point. It helps us converge to the minimum better. If anyone else has any questions, go ahead. How does this relate to the loss we found for 0 and 1? Okay, yeah, for sure. So the loss we found for 0 and 1 was that log loss function. And when you take the derivatives of it, you actually end up getting these as the gradients of it. So what you do is you take that, you take this loss function over here, take the derivative, and you end up getting your partials for W and B. Okay. Okay, great. Are there any other questions?
Yeah, I have a question.
Yeah, go for it.
So you were talking earlier about how log makes the function, the loss function, smooth to like make the gradient descent nice, like over a function that grows really fast, like for instance, e to the x or something like that. So is it better to like make your function decrease slower by modifying the actual loss function, or is it better to like increment slower by having a small learning rate?
Okay, so I see what your question is. So there are two aspects to this, right? It's like once we've chosen a loss function, then we do the best we can and we take these small steps. So suppose we've said blindly that mean square error is the best possible loss function. Then if we are in fact oscillating, we need to take these smaller steps. But this is once we've fixed the loss function. On the other hand, what we could do is we say, I'm going to carefully choose such a loss function so that it's as smooth as possible. So sometimes if you choose a bad loss function, you get all these local minima, and that's not good for optimization. So there are two different steps, and both of them are obviously important, but it's like saying if your function itself isn't smooth, then taking these small steps isn't going to be very helpful. So the correct loss function is pretty important.
Okay, that makes sense.
Awesome.
And one more question, super fast. Is the only reason you don't want, like, would you always want to have your loss function be as small as possible? You're just like, are you just constrained by computing power? Like, would it be best to take really tiny steps if you had like an infinitely powerful computer that could compute them all really fast? Okay,
so when we say steps, right, all I mean is this alpha parameter over here. That's the step size. So that isn't going to be dependent on computing power at all. It'll run the same on any computer. So we can choose it as 0.1 or 0.0001. And that will tell us how small the sizes are. Yeah.
If you made it really small though, wouldn't it take longer? Like if you already had a sufficiently small value and you made it smaller than that, wouldn't that mean that it would take more iterations of gradient descent to get to the minimum?
Okay, I see what you mean now. Yeah. So it'll definitely take more iterations, but the principle is always slow and steady, because what happens is if we try converging too quickly, like we mentioned last workshop, we start up oscillating all over the place and we never end up at a minimum. So yeah, definitely. If you have a large computer and you have all these infinite resources, then it does make sense to take these small steps, but there's a slight caveat. We don't want to take too small steps because you have no idea where you are, right? So if you end up take a small step and you're like, I have not really improved, so you don't see any difference in your cost. So there is a balance to be achieved, but it definitely doesn't mean go too small or too high.
Okay.
Great. Are there any other questions? Yeah, so someone brought up a good question in the chat. It might fall into a local minimum if the step size is too small. And yeah, like you mentioned, if we are somehow stuck in one of those local minima, we're somehow stuck in here, we want to try and get out of it. So in that case, a large step to jump out of it would be pretty helpful. So that's really great. Okay, are there any other questions? Okay, fantastic. So just to quickly reiterate, we have our cost function, which is log loss. We have our parameters, which are W and B, and we update W and B using the gradient. We keep doing this, keep doing this, keep doing this, and eventually we get the best possible W, the best possible B, which is the answer to our classification problem. And that's it. That's our workshop for today. So thank you so much for coming. Please, please, please fill out our feedback form over here. It's B-Track Feedback 3. Next week, we're going to be talking about multi-class classification and k-nearest neighbors. We have a really cool joke over here. If you want to understand it, come to our next workshop. And definitely socially distance. All right. Thanks a lot for coming. Feel free to stick around if you have any questions.
Oh yeah, I have a question.
Oh, go for it.
Where do we put the event code?
So you go to the ACM membership portal. I think we have a link for it in the first slide, if I'm not mistaken. Let me check that out real quick. Oh, we don't. I'm sorry. Basically, if you go to the ACM membership portal, you can enter this code and get points for attending the workshop.
Yeah. I
Okay,
found the
perfect. We'll send it on
Okay.
chat.
Yeah, thank you.
Yep, no problem.
About like, I have a question, but not really a question. I just want to make sure I understand today's content. So like, for like, we get like the output, like W and B are two output from the old linear regression we got, and then we take it as input and put an activation function on it to determine whether it's like to make a category, to get a categorical output, and we want to minimize the error, so we put a binary cross-entropy loss function on it, and then by doing that we keep updating the W and B so that we can keep minimizing the loss.
Yeah, absolutely. That's absolutely correct. It's a great summarization, and that's exactly what we're doing.
Okay, thank you.
For sure.
All right. So someone asked what function is minimized when finding the best W and B. So for logistic regression, that would be our log loss. But I guess for machine learning in general, it would just be the loss function of choice that's being used.
Yep. I'm gonna stop this recording.